So today is October 1st, and what you're looking at right now is an announcement sent by the Career Center. There is a Business and Technology Career Fair on Wednesday, October 14th from 12 to 2. This is during your free hour, so you should attend. It's open to all majors and it's held virtually. So it really is in your best interest to attend something like this. There are going to be employers that are recruiting for open positions. So have your resume ready and cleaned up, and it's a great place to network, get to see what's available. Again, it's open to all majors, although it's called the Business and Technology Career Fair. You have to register to attend at qc.cuny.edu/hireqc. They say to dress professionally because you're on a Zoom call. And if you want to take a picture of this, I'll try to remember to send this as an announcement and also post it on my lab. Detrick, you say you have a question? Yeah, go ahead. You can use your audio. So the question one is Excel 1 graded and uploaded on Blackboard. So I did not grade and upload on Blackboard. Instead, I graded and sent everyone an email regarding their score. So you can ask your teammates what the score is, and everyone gets the same score. As long as your name is on the assignment that is uploaded. Okay? And if you can't get that information, you can send me a separate email. Okay, so we're going to continue with chapter 5. And with chapter 5, we were talking about probability. And in the last class, I think we stopped at, let's see. We talked about calculating probabilities using different formulae. And this was the last example that we worked on, calculating all these various probabilities. So today I'm going to continue with calculating probability, but showing you how to do it using a different method, using a table. So rather than an example that you see like this, we're going to look at a contingency table. So if you recall, we did hear this word before, contingency table. It's basically a cross-classification table with rows and columns. So one variable is contingent on the other variable. That's why we call it a contingency table. So looking at this example here, as part of a Pick Your Prize promotion, a store invited customers to choose which of 3 prizes they'd like to win. The responses could be placed in the following contingency table. So it's well organized here. You're looking at the total number of people that were asked, and that's 478. So your sample would be 478, a collection of all possible outcomes. Out of the 478, 251 were women and 227 of them were men. So they asked them which prize they preferred. Did they prefer an MP3 player, a camera, or a bike? So 247 of them said they preferred an MP3 player. 60 of the men preferred a bike, and so on. Okay, so it's nicely laid out, and now we're going to calculate different probabilities. So the first probability we're going to look at is something called marginal probability. It's exactly what you think it is. It's something that's calculated in the margin, marginal probability. So if I look at the margins of this contingency table, what's in the margin is my total column and my total row. So for me to calculate marginal probability, that means I'm calculating the probabilities in the totals. So if I go to the next slide that explains marginal probability, So that's this. If I wanted to know the marginal probability of man, I would do 227 divided by 478. If I wanted to do the marginal probability of camera, I would do 141 divided by my sample space of 478. So that's all it is. Probability is calculated in the margins of the table. Okay, so going back now to our previous slide. So that's number one. Number two is simple event. So let's define this first. A simple event has only one characteristic, simple event. So let's suppose you're asked to find the probability that the respondent chosen is a woman. Okay, so before I do that, let me write up here. Let's assume woman is A and bike is B, just to make it easier. Okay, so you're asked to find the probability that a randomly selected person is a woman. So find the probability that the respondent chosen is a woman. Now this is only one characteristic. The person is a woman. So that's considered a simple event. So I could rewrite this in a different way, saying I have to find the probability of A. Now referring back to our previous formula, to find probability, the numerator should count all the possible outcomes in this event divided by my sample space. So if I look at woman, what's the total number of outcomes for woman? Gilbert, what do you think that answer is? So my numerator would have the total number of outcomes for woman. Abraham, my numerator would be 251 divided by my total sample space of 478. Yep, that's it. Okay. Yes. So Gilbert, that's right. So that's my simple event, looking at one characteristic. The next thing is complement of event. So complement of event just means the opposite. Complement means opposite. So if you're asked to find the probability that the respondent chosen is not a woman, okay, so you're asked to find the probability of woman complement, right? So that's the opposite, woman complement. That means you're asked to find the probability of A complement. So you can do this in two different ways. Jason, can you suggest one way? Na Young, a different way? So one way of doing it would be taking the total number of outcomes for the opposite of woman, which would be 227, and divide it by my sample space. Yes, that's right, Ying. And the other option would be, actually, we didn't finish this, right? Yep, let's go back here because I didn't finish this example. Abraham, do you want to give this to me? What's 251 divided by 478? What do you get for that as an answer?
0.5251. It's a decimal.
5.527. Okay, that's good. So that was our answer for simple event. Coming back to complement of event, I said one way of doing it is taking the total number of outcomes for not a woman, opposite of woman, divided by the sample space. Or you could do 1 minus, yep, Xiaoting, that's right, 0.525, which is what, Quasi, what do you get for that answer? MD Morshed? I think it's 0.475, right? Okay. So now you've got complement of event. Yep, thanks. Any questions about this? So recognize that you can do this in two different ways. You don't only have to do it one way. Both ways give you the same answer, but recognize that. So I know it's very easy to understand that complement means opposite, but you need to know which events we're talking about and which values you're taking from the contingency table. Okay, the next thing is joint probability. Now, first to define this, joint means two or more characteristics. So for the purpose of this course, we're only looking at two characteristics happening at the same time, not more than two. So joint probability is a probability that the respondent is a woman and chooses a camera as a prize. So we have two events happening at the same time, woman and camera. Okay, so let me write this. You're asked to find the probability that the respondent chosen is a woman and selected a camera. Okay, so if I change that into A's and B's, that means I'm finding the probability of A and B. Okay, so now again, according to my union A and B formula from before, the numerator says I need to see whatever A and B have in common. So what A and B, woman and camera, what do they have in common? What value is that, Mark? Okay, Christopher, you say 91. Okay, divided by what? Not 141. Yes, Christopher, I'm going to go with you. Remember, you're dividing it by your sample space. So out of all the people who were part of this experiment, what's the probability that the one I pick is a woman and chooses a camera? So out of the 478, 91 would be my answer. And did someone give us the answer for that? 0.19, Kathleen. Okay, so let me type that in here. Okay. Any questions so far? Let me see what else I wanted to mention here. I think that was it. So right now, this stuff isn't new, really, other than marginal probability, simple event, joint probability. The next thing that I want to talk about is something called conditional probability. So the next slides, actually, I skipped a couple of slides because the answers are there. It just shows you exactly what we did. So now conditional probability. So what exactly is conditional probability? In general, want the probability of an event from a conditional distribution, we write probability of B given that A has occurred and pronounce it the probability of B given A. A probability that takes into account a given condition is called a conditional probability. So quite a lot happening here. Let me mark it first. This is the formula that you're looking at. Probability of B given A. So this long line here is read as given that. So given that event A already occurred, what's the probability of B occurring? So again, we're saying given that this event already occurred, what's the probability of this event occurring? So the formula, now you don't need to memorize the formula because you and I know that it's sort of an open book test. You have free access to conditional probability formula. So the formula says the numerator is the probability of A and B, whatever A and B have in common, divided by the total probability of the event that already occurred, the probability of A. Okay, so make sure you understand what's going on with conditional probability. It's the probability of one event occurring given that another event already occurred. So given that this event A already occurred, what's the probability of event B occurring? So let's go back to our example with the contingency table. Question is saying, what is the probability that a randomly selected customer wants a bike if the customer selected is a woman? So you already know that the customer selected is a woman. Now, what's the probability that the customer wants a bike? So I'm going to write this up here again. We initially said that woman is A and bike is B. I'm going to stick to that again. So probability, so what's the probability of bike given that the customer is a woman? So I'm just rewriting this so I can understand it for myself. B is bike given that person is a woman, right? So again, rewriting this, I'm saying B given that A. So according to the formula, the numerator has to be whatever woman and bike have in common. So woman and bike have in common. And then divide that by the total probability of woman. Okay, so let's do that together. And let's see. Shemaya, you say the numerator. So looking at my formula box here, the numerator says whatever A and B have in common. So woman and bike have in common. You're saying 30 is what they have in common. And then you have to divide that by the sample space, correct? So that's just my numerator. And then divide that by the total probability of woman, which is 251, divided by my total sample space of 478. So that's correct. Shemaya, you're right. If I had to rewrite this, I would do 30 divided by 478 times, and then flip it. 478 divided by 251, the 478s would cancel, and then Christopher, you're right, that would be 30 divided by 251. So in the future, I will set second step and go straight into 30 divided by 251 because it's understood the sample space cancels out. Okay, so with conditional probability, this is really what you're doing. And can I have an answer for this? Okay, Diana, you say 0.118. Okay, so what does this mean? This is telling me that suppose you randomly selected a woman. What's the probability that the woman would select a bike? Well, the probability is 11.8% or 0.11. So that's the meaning of conditional probability. Questions for me? Okay, so let's move on. This is giving us the answer. It's the same example I just did. Now I'm going to move on to probability of A or B. So we did probability of A and B. Now we're going to look at probability of A or B. So reading, when the behavior is not mutually exclusive and occurs at the same time, then the general addition rule can be used. So not mutually exclusive. It actually does occur at the same time. So it's possible that the person can be a woman and can choose a bike. So it's possible for both to happen, both events to occur at the same time. So now the question is asking you, what's the probability that you randomly select an individual and that individual is either a woman or chooses a bike as a prize, A or B? Now in math, when you see the word or, it means addition. So according to our formula for addition, A or B, that's really intersection. It's the total probability of A plus total probability of B minus whatever they have in common. So I'm not going to write it because it's here at the bottom here. Total probability for woman is 251 divided by 478 plus total probability of bike is 90 divided by 478 minus whatever they have in common, 30 divided by 478. So that could be everything divided by 478. So that probability is 65.1%. Questions for me? So remember, this means that it's not mutually exclusive. It could happen at the same time. If you were not sure whether or not it's mutually exclusive or not, and you didn't know whether you should use the general addition rule or the regular rule, well, if it is mutually exclusive and it cannot happen at the same time, then they would have this entire thing equal to 0. They have nothing in common. It cannot happen at the same time. It would have been 0. Okay, so that's just a thought on the side. So far, we've covered a lot already. We did simple event, complement event, joint probability, conditional probability, and we did this with intersection. The last thing I want to show you is going back to that term, independence. Dong Yang, you're saying, how did we get 90? So if I look at total probability of A is total probability of woman, that's 251, plus total probability of B is the total probability of bike, that's the 90, minus whatever woman and bike have in common, minus the 30. That's how we got that. Okay, so moving on, going back to that term independence. Now we've seen that before with categorical data, when you looked across a contingency table to figure out whether the two variables are independent or not. But that was it was not really objective. So that was not the ideal way. We went back to independence when we looked at our X and Y variables to figure out if they were independent of each other or whether there was a strong association or correlation. We're going to revisit independence again here, but this time we're actually going to prove statistical independence. Now, in order to prove statistical independence, you need to have a formula. And with this formula, you're going to try to prove whether the left side of the equation is equal to the right side of the equation. And if it is equal to each other, then you have proven statistical independence. You're saying that the two variables are independent of each other. Okay, so now recall, what exactly is independence? Independence exists when the outcome of one has no effect on the outcome of another. Outcome of one variable does not affect the outcome of another, does not depend on the other. So the question is, are price preference and sex independent of each other? These two variables have nothing to do with each other, or does it depend on if you're a man or a woman, what your price preference is? So that's what the question is asking. So you need to prove it. You can't just look across the row and make a decision. You actually have to prove statistical independence. So this is the formula that you're going to use. Is probability of B given A the same as probability of B? So this is the left side of your equation, and this is the right side of your equation. So the idea is to prove that they are equal. So in other words, you're trying to say probability of B given that A has occurred, is that equal to the total probability of B? And I'm going to write this again here. We had woman as A and bike as B. I'm just sticking to the same thing. Okay, so this is what we need to do. We need to prove whether this left side is equal to the right side of the equation. So let's start with the left side of the equation. So we have probability of B given that A has occurred. Now we already did this in the last slide, so we can use the same information. Remember the numerator for this formula, conditional probability, is whatever B and A have in common. So I'll write it out. B and A divided by the total probability of A. Okay, so that was the formula. Now in our example here, the numerator is what do B and A have in common? What do woman and bike have in common? What's that value? 30 divided by the total probability of A, total probability of woman is 251, and we got 0.118. Okay, can everyone mute themselves, please? Okay, and then the next thing, so this is the left side of the equation that we just did. Same thing as before, nothing new. Now the right side of the equation, the probability of B. Okay, what's the total probability of bike? What's that value? Total probability of bike is 90, Oscar. Okay, thank you. Divided by, Diana, you said 478. Okay, and what's the answer for this? Lisa, you said 0.188. Okay, so now question is the left side equal to the right side? It's the answer is no, it's not. It's a little hard to see if you're looking at all these different numbers, but correct. It is not equal to. So I'm going to say it is not equal to, which means it is not independent. Okay, so going back to our question here, are the two variables independent of each other? No, they are not independent of each other. There is some dependency because the left side of the equation is not equal to the right side of the equation. There is some dependency. So that means the price that is preferred has something to do with whether you're a man or a woman. There is some dependency. Does that make sense? So if you were calculating this, trying to prove the left side equals the right side and came out to be equal, then you would say they are independent and they have nothing to do with each other. But that's not the case here. So yes, you're comparing the two ratios, Christopher. Yep. I think that's it for this. So what I wanted to mention is make sure when you're doing this, even for the homework, be very careful with your B's and A's. So B and A have to be two different variables. So B has to be from this set and A would have to be from this set. And then this B would have to be the same event that you chose on this side. So be very careful and don't try to do A and B from the same variable. It would not make sense. Okay. Any other questions for me? So Jason, your question is, can you repeat which side has to be B and A? It doesn't matter. So I'm going according to how the question is asked. Price preference. So for that reason, I'm going with B. That's the first thing, my price preference. B is the first variable. And sex is the second variable. So I would choose that. So it doesn't really matter, but make sure it's not from the same variable. That's all it is. So there are a few examples in your textbook. And also there is another example in the next few slides, which I'm not going to cover, but you can see how it's done on your own. So I'm going to skip those slides because I think it's quite self-explanatory. There's extra examples in the textbook. There are practice homework problems that you can do as well. I'll leave this up here so that you can read this on your own. What I want to focus on now is showing you a third way of calculating probability. So the third way of calculating probability is using a probability tree. So let's go back again. The first method that I showed you in the last class was giving you a formula. The second method is what I did today using a contingency table. The third method is probability tree. Now you've probably seen this before in a previous math course. You might have called it a decision tree. They mean the same thing. And it's called a tree because it looks like branches of trees and you're calculating probabilities for different events. Okay, so I'm going to start a new example with a blank screen and a reminder that every time you put your answer in the chat box or you turn on your audio or you respond to a question I ask you individually, all that is recorded and I can download it as a report. So you do get credit for participation and that goes towards your course grade, right? So just a reminder about that. Okay, so let's start with a blank screen and I'm going to type up my example here. So the example is about probability trees. Let's fix that. Okay. So then typing here, suppose we toss a fair coin 2 times. And let's say you can get heads or you could get tails. Okay, so that's the question. You're going to have to draw a probability tree and the experiment is we toss a fair coin 2 times. Now why fair coin? Fair coin because I'm deliberately saying that there's only 2 sides to this coin. One side will be heads and the other side will be tails. And we're tossing it 2 times. So now we're going to draw the probability tree. So first I have the first time that I toss the coin, and then I have the second time that I toss the coin. Okay, so here I'm drawing the probability tree. When I toss that coin the first time, there's 2 possible outcomes that I can have. I could have either heads or I could have tails. Then the next time I toss my coin, it's the second time. If I had heads the first time, the second time I could have heads or tails. And then if I had tails the first time and I toss my coin again, I could have heads or tails. Okay, now let's calculate the probabilities. So the first time when I toss my coin, what's the probability of getting heads? Diana, how did you get 50%? So 50% is correct, but there are only two options, so 1 out of 2, Brandon says, so I agree. So the probability of getting heads, if you want to use your formula, is you can get 1 head out of 2 possible outcomes, or 0.5, or 50%. Okay, so that's how you would calculate probability for getting heads. When you toss that coin the first time, what's the probability of getting tails? Karina, same thing. You can get 1 tail out of 2 possible outcomes. So that answer is 0.5 or 50%. Okay, how about the next one? Next time I toss my coin, let's say the first time I got heads. What's the probability of getting heads when I toss my coin the second time? Priscilla, why do you say it's 0.5? So you can turn on your audio if you want to explain. Jennifer, you say heads would be 50 as well. Anyone want to explain why it's 50%?
There's still only like two sides, so you still have a 50-50 chance of getting either heads or tails.
Okay, sure, I'll go with that. So still, you're saying you can get 1 head out of 2 possible outcomes, so the answer is still 0.5. So for that reason, I'm going to say, Urmila, it's not 0.25. There's an assumption going on here. We're saying that what happened previously will not affect what will happen next. What happened the first time is not going to affect what's going to happen the second time. So it doesn't matter if you had heads or tails the first time. It does not affect this coin when I toss it the second time. I'm still going to get 1 head out of 2 possible outcomes. So for the same reason, the next probability is also 50%. This is also 50%, and this is also 50%. Okay, so now a few questions. Let's start with the first question. What's the probability of getting heads both times? Of getting 2 heads? What's the probability of getting 2 heads? What do you think the answer is for that? So I'm asking, what's the probability of getting heads the first time, heads the second time? And Oscar, Eugene. So Karina, I'm only flipping it 2 times, right? First time, second time. And Eugene and Oscar, you said you take 0.5 for the first time times 0.5 for the second time, and that's how you get the 0.25. Agreed. Okay. Let's do another one. So this is 0.25. Next question, what's the probability of getting 1 head? So the probability of getting 1 head means I get heads the first time, tails the second time, and then or I get tails the first time and heads the second time, right? Tails the first time, heads the second time. Okay. So how do I answer that question? What's the probability of getting one head? Remember, the probability of getting one head means I get heads the first time or heads the second time. So, Shemaya, how did you get 0.5?
Isn't it the same as though as if you did like probability of heads or probability of just tails? It's just
Yeah.
0.5.
Okay, so your answer is correct. So that means that is that 0.25 plus 0.25. Yeah. So that's how you get the 50% or 0.5, right? Let's do one more. Find the probability of no heads. So again, you can do this in a
Professor,
couple of, yeah.
you say it's 0.25 times 0.25?
Which one are you talking about? For this, for the second one?
Yeah.
No, I'm saying I took heads, tails plus tail heads. Got it? Does that make
Oh,
sense?
okay. Got it. Thanks.
Yeah, I took this plus this because I'm saying heads the first time or heads the second time. So that or word, again, going back to math, you're
Addition.
adding it. Yep.
Okay. Thank you.
So now probability of no heads is the same thing as saying probability of both times getting tails, right? So same thing is 0.5 times 0.5 is equal to 0.25. Yes. So I think you guys got it. So it's really what you need to understand is that there's this assumption going on that they're independent events. The first time has nothing to do with the second time. They're independent of each other. Because if I said that whatever happened the first time is going to affect what happens the second time, then our probabilities are wrong. It would be incorrect. Okay, so the way we did this, we're saying they're independent of each other. So any questions? This is really the last slide that I have for this chapter, but I would like to do something else with you. What I'm going to do now is I'm going to put you in breakout groups, and I'm going to give each of your groups a small probability problem, and I would like you to work on the problem with by drawing a probability tree and calculating the probabilities just the way we did. And then I'll bring you back into the main room and you're going to show us the answer, how you solved that probability tree. Okay, any questions for me? Okay, so I'll put you in, let's see, we can do about 9 groups, I think. Let's see. Uh, 10 groups. Let's put you in 10 groups. And so it's going to take a while for me to go to each group and give you the problem, but bear with me. And it's not the same group as your Excel team assignment because this is done randomly. So you're with different people. Okay, you can turn on your audio. If you cannot use the whiteboard for some reason and it keeps erasing, have a piece of paper in front of you so that when you come back to the main room, you know what to share with us. Okay, so putting you in groups now. And before I forget, you'll have about 10 to 15 minutes to work on it. Okay, one of you is on a phone and I won't be able to put you in a group. So you would have to log out and log in through a computer to be able to put in a group.
Oh, there we go.
Can everyone hear me? You're back in the main room now?
Yes.
Yeah.
Okay. Hopefully that was enough time. Let's start with the first group. So let me clear this out and I'll share your question. So this was your question about boots and trainers with a choice of wearing a cap or not. So who wants to start with that? Okay, and I'm typing up here saying this is probability tree number 1. Okay, so we're saying that he has a choice of wearing boots or trainers, and he also has a choice of wearing cap or no cap. Okay, and you're given a few probabilities. Yes, so the probability of wearing boots is 0.4. And automatically, you know, 1 minus 0.4 is 0.6. You're given 0.7. Yep.
Really quickly, so what me and our group found was obviously like we're giving some probability, so it's really easy to find the opposite. I mean,
Yep.
the comparative value given the initial value, and
Yep.
we can see that this is the reason because he obviously has some biases
Yep.
between boots and trainers and the outfits he likes to wear. So it's just a numerical representation of that bias or that opinion.
Yes.
And that's just the link tree we got.
Perfect. Thank you, Group 1. So that's very similar to the homework that you would be getting for this chapter too. So it's good practice to do that. I just posted the second one. So Group 2, you can start typing it in. So this is probability tree number 2. So this one is about cupcakes. So feel free to draw it in. I can start it off for you. You have choice of 2 kinds of cupcakes, right? Either chocolate or plain. So you have chocolate or plain. And then if she had another cupcake, she could again choose chocolate or plain. Do you have probabilities set up for this? Did anyone have this ready? So group 2, I'm not getting a response. Okay, so if she chose a cupcake the first time, it's out of 5 cupcakes, and she was told you could get 2 out of 5 for a chocolate, or you could get 3 out of 5 for a plain cake. The second time, what was it? You could choose 2 cupcakes now out of 4, and this was also 2 out of 4 if she had eaten chocolate already, and this one would be 2 out of 4. And this would also be 2 out of 4 for a plain cake. Okay, so I need to have at least one person from each team either draw or explain. Okay, so I didn't have anyone from group 2. I'm moving on to the next one, which is about games. Jane and David playing games. So I'm posting it here. And we're going to clear this out. So feel free to start typing it in.
Okay, I'll draw it really fast.
Yep. Go ahead. So we're talking about Jane and David playing 2 games of golf. Either Jane wins the first one or David wins. And then the second one, second game of golf, you could have Jane winning or David winning. Yep, that looks good. And then the probabilities. 5 out of 6, yep. Perfect. Does anyone have any questions about this? So again, all this is being recorded. If you're confused with probabilities, I suggest you go back and take a look at the examples in the chat box and the trees that are being completed. So that's completely accurate. Thank you for that. This is the next one. It's about professional basketball. So let's erase this so that you can start writing this in. This is probability tree number 4. So who wants to start? So this is a little different, I think, right? Probability tree number 4 says proportion of people who become professional basketball players. Okay. What do you have for probabilities? So actually, I'm going to ask you to stop because I think the first tree is missing here. Okay, so let me stick that in there. So I'm going to say that you should probably have, let's call it professional basketball player. They call it a PI, right? Let that be a PI. And yeah, exactly. And I think you would be missing one here saying it's not a PI. So this would be not PI. So either they are a PI or they're not. Either they're professional basketball players or they're not. And if they're professional basketball players, you're told that the probability is 0.0001. So start with that. Okay. And then go ahead. So either they're a professional basketball player, so the probability of being a professional basketball player is 0.0001 or not. Okay, go ahead. And then the probability of being a professional basketball.
I'm kind of lost.
Okay, yeah.
From the
So I'm reading the question. So it says here the probability of being a professional basketball player and being black is 0.842. Okay, so that I got straight from the question. The question also says the probability of being white and being a professional basketball player is 0.1%. 0.001. And then N represents others, so that at this point you would do 1 minus the 2 remaining. So the question is asking you, draw a probability tree that shows the percentage of being black and this. So I would do being a professional basketball player times 0.842 would be the answer to that final question. Okay, so that's all you needed to do. 0.001 times 0.842. Okay, so I'm going to move on to the next one. Okay, that's this one with Democrats and Republicans. So please start drawing. Okay, thank you. We have Republicans, Democrats, and Independents. Okay, and we're told if you're Republican, either you're for the tax, so yes or no, or for, or, no, or against. Okay, and then you're given certain probabilities.
So it's 33 by 100.
Say it again.
33 by 100, 44 by 100, and 23 by 100.
Republican is 33. Yep. Democrat is 44. And independent is 23. So the question was asked, person is a Democrat and not in favor, right? So which one would you do? Democrat and not in favor.
So
You would do the 44% for the Democrat.
okay,
So I can write it here for you. So this is 44%, right, for the Democrat, because that's given to you in the question. And then you're also told in the question, of the Democrats, 66% are in favor, right? So the balance would be against. So that would be 1 minus the 66%. Yep, that's the 34. So that's all you have to do. Yep. So you do this times this, and that would give you your answer. Okay. So now moving on to the next group, probability tree number 5. It's about these manic mango games. So let's erase this, tree number 5. And you can go ahead. Okay, so that looks right. We have game 1 and game 2. Either they enjoyed it or they did not. Okay. Okay, so that was 60 and 40. Yep, that's it. You got it. So exactly what you're asked to do, that's correct. I'm going to move on to the next one, which is group number 7. So group number 7. It's about getting vaccinated for COVID-19 or not. So either yes, you're inoculated, or no, you're not. And if you do get inoculated, either they live or they die. So we should be finished in a few more minutes. Okay, I understand if you have to leave, but I'm going to keep recording this so you can always go back and refer to it. We have a few more groups to go on. So yes, that's 3.9%. So if they get vaccinated, so let's say 3.9% of the US population got inoculated. So then we know the balance did not get inoculated. Okay, so N is fine, no inoculation. And then either they lived. So we're told that for those who were inoculated, 97.54% lived. Okay, so here you would type in 97.54, right? And the balance did not live. So, and you're also told that out of those who were not inoculated, 14.11 died. So to answer the question, how many would live if they were not inoculated? So not inoculated, and how many would live? So that's your answer. 85.89%. Okay, questions for me? Nope. Okay, moving on to the next one. That was good. Thank you.
Thank you.
this is about colors, school colors. So this is probability tree number 8. So you can go ahead and do this. I think I skipped one, but we can go back to it. So this is number 9, but this is actually number 9, question number 9 question. So let's make this number 9. Okay, so this is group number 8. Sorry. This should be group number 9. Okay, so group number 9 was having the one about the colors. So you can go ahead and write that. Yes, so either you were given a choice of green. Yep, that's it. And the second option is if you chose blue, then you would have to choose yellow or red. Yeah. Yes, and if it's yellow or red, and then the other one was if they had green and they chose red, it would be I think, is it 30 or 55? This should be 55, right? So just fix this value. Other than that, it's correct. Yep. Did you have any questions for me? Okay. So that value should be 55, but other than that, it's correct. I'm going to the one that I missed before. This is group 8. So you can go ahead and do this. Right, we have the National League with the Dodgers and the Braves. And that's 54% and 46%. Yep. Does someone want to explain?
Lots of baseball stats in here.
And then American League, you had the Rays and the Yankees. Okay. And what did you get for the probability? .42 for the Rays. Okay, 58, 48, 52. Looks good. So who do you think is going to win the World Series? That was a trick question. You didn't have to answer that. Thank you. Good. That looks good. Any questions for me on this? No? Okay, let's move on to the next group. This is probability tree number 10, I believe. Okay, this was the one about rain or not. So either rain or no rain the next day. The numbers, I can't really see what the numbers are. Can Can someone use their audio to explain what those numbers are for probability?
Oh yeah, I could. There's just some construction going on in the background, so if you hear that, I apologize.
Okay. Yeah, no, that's fine. What did you write for the number for no rain?
1/3 for rain.
Oh,
So it
okay.
says
Oh,
it,
got
and
it.
it's 2/3 for no rain. It's
Okay, got it. Yeah, yeah.
and then the second one is gonna, like, the bottom left is gonna be what's it called? The bottom left is gonna be, sorry, for the top is gonna be 1/5. I apologize.
Right.
One
Okay.
fifth,
Yeah.
and this is supposed to be 4/5.
4/5. Got it.
And then
Right. Yep.
this is supposed to be 1/3, and then this is supposed to be 2/3.
Yep.
And this is no rain, and this is rain, and then this is supposed to be where it says 1/6, and this is supposed
Okay.
to be 5/6.
Perfect. Yep.
Same thing
That's it.
with no
You got
rain
it.
and rain. Yeah,
Perfect. Thank you for that.
no problem.
Next one is probability tree number 11. Okay, so this is the one about COVID and testing positive or negative. So this is saying if someone tested positive, if someone has it and tested positive or negative, someone does not have it, tested positive or negative. Okay, you have it or you don't have it. Okay, so if you have it, either you're tested positive or negative. Okay, so this is 99% you don't have it.
Professor, do you want me to explain?
Yeah, okay, yeah, go ahead.
Sure. So if you have it, then which is positive, right? It's a probability of 0.01%. And then if you don't have it or negative, it is 0.99. Then if you, I mean, if it comes out positive twice, which is 0.01 times 0.01, which is the result is 0.0001, and that's the probability. And then if it comes out, the probability that if it comes out positive and negative equals to 0.01 times 0.99.
Okay, so that
Now,
just to answer that last question, how likely is a patient to have it and test positive? So you have it and you test positive, that's your 0.01 times 0.01, correct?
yes,
So
correct.
yeah, that's the last one on the top. Okay, just waiting
So,
for that number.
do you want me to continue? Or
No,
it's
I'm
fine?
just waiting for the last one. No, that's
Okay,
good.
the
That's
last
what I was
one?
waiting for.
All right, if
Yeah.
it comes out like positive twice,
Uh-huh.
okay, it's 0.01 times 0.01.
Exactly. Yep, that's perfect. Thank you very much.
No problem.
And this is the last one for probability tree number 12. So
Yep.
let's do
So
that.
we did a drug test. We had a sample size of 1,500
Okay.
players.
You
We
can draw it
had
on this.
a drug test, which was either positive or negative. And then the positive test was either a true positive or a false positive. And the negative test was either a, 1 second, my computer's doing a thing, okay. The negative was either a true negative or a false negative. The positive was 6%, 6%
6%.
or 90 players. The negative was 94% or
Yep.
1410 players. The true positive was 95% or 85.5 players. The false positive was 5%, which was 4.5 players. The true negative was 10% for
Okay.
141 players, and the false negative was 90%. Sorry, I have those backwards.
Yeah, that's okay.
Yep.
I got it.
Okay.
90, 94.
1269.
Right.
So
Yes.
the positive, the false negative and the true negative should be flipped.
Perfect. Thank you very much. So all you had to do is just add on those branches and it's right. Yep, so that's it for today. Don't forget to submit your Excel to assignments and practice the rest of these exercises in your homework. Okay, enjoy the rest of your day.
Thank you.